Every phone, every laptop, every AI server that you hear about today runs on one material, and that's silicon. But here is the strange part. Silicon is not the fastest semiconductor out there. It's not most exotic material. And in some categories, it's not even the top performing material. Then why does the entire modern world's technology still depends on it? Engineers have known for decades that other semiconductors can beat silicon in specific ways. For example, gallium arsenide can move electrons faster. Gallium nitride can handle high power and high electric fields, whereas silicon carbide is excellent for harsh and high temperature environments. If better materials exist, then why didn't the industry move on? To understand this in a better way, let's go back to 1947. Bell Labs. Three brilliant physicists, Bardeen, Breton, and Shockley, just invented this transistor. And the material they used, it wasn't silicon, it was germanium. Germanium was the favorite semiconducting material of early electronics. It was easier to purify, it had better speed, and honestly, it worked. The early transistors, early radios, and all the computers at that time were made up of germanium. The question is, then what went wrong that people moved from germanium to silicon? Well, imagine you have got a sports car, it's fast, it's responsive, it looks great on a test track, but the moment you take it on a cross-country road trip in the middle of summer, the engine overheats, the performance drops, and eventually it just stops. And that was the biggest problem of germanium semiconductor. It couldn't handle heat because of its narrow band gap. We'll talk about band gap in a minute, but before that, let's try to understand its consequences. At room temperature, all the devices, all early computers that made of germanium were started leakage current. And leakage current has direct consequences of data loss. So in a real world application where temperature is little bit high, germanium wasn't reliable. Meanwhile, a few engineers at Texas Instruments and Fairchild Semiconductor started experimenting with silicon. It was harder to work with, harder to purify, but once they figured out very high purity silicon fabrication process, something remarkable happened. The engineers realized that silicon is much more reliable than germanium. It could work in extreme heat, in military hardware, and in industrial machines. In 1958, Jack Kilby at Texas Instruments built the first integrated circuit. And a few months later, Robert Noyce at Fairchild made another integrated circuit using silicon and a process that could actually scale. Then that was the moment everything changed. Silicon didn't just win the race, but it redefined the rules. Alright, let's talk about what makes silicon special at the atomic level. And it starts with something that I mentioned before, band gap. Every semiconductor has a band gap. It's basically the energy barrier that electron needs to overcome to start conducting electricity. Think of it like a door. If the door is too easy to push open, electrons flow through whenever they want, even when you don't want them to. And that's leakage current. And it's a nightmare for chip designers. If the door is too hard to open, you need tons of energy just to make anything work. That's great for insulators, but terrible for transistors. But silicon's band gap is just 1.2 electron volts, and that lands right in the sweet spot. At room temperature, silicon barely leaks any current. But applying a tiny voltage, electrons flow where you want them. And by using this mechanism, we can turn switch on and off billions times per second with minimal leakage current. And that's the Goldilocks of semiconductor industry. And here is the kicker. Silicon is incredibly easy to dope. That means you can precisely add impurities like phosphorus or boron to control exactly how it conducts and how much it conducts. More control means more complex circuits. More complex circuits means, well, everything from smartphones to spacecraft. Now let's talk about heat, because in real world application chips get hot, really hot. Your phone processor can heat 80 to 90 degrees Celsius under heavy load. Data center servers run around 70 to 80 degrees constantly, and military electronics even higher. And this is where germanium completely fell apart. Germanium's small band gap means that as temperature rises, more and more electrons get enough energy to jump across on their own. And by about 75 degrees Celsius, a germanium transistor starts losing its ability to distinguish between on and off current. And that's a death sentence for a digital circuit. Silicon, on the other hand, stays stable up to 150 to 200 degrees Celsius in most of the applications. Silicon spreads heat efficiently without letting hotspot build up. Remember our sports car analogy? Here, silicon is like a truck, which is reliable on any type of road. Okay, now let's go to the silicon property that, in my opinion, is the single most important reason for silicon dominance. And it's something that most people have never even heard of: silicon dioxide. When we expose silicon to oxygen, it naturally grows a thin layer of silicon dioxide, and this layer is extraordinary. It's an almost perfect electrical insulator. It bonds to the silicon surface with virtually zero defects. It's chemically stable. You can grow it to any thickness you want with incredible precision. And it's the foundation of MOSFET, which is the building block of every modern processor. But silicon dioxide is so good that an entire manufacturing revolution was built on top of it. Without silicon oxide, there would be no MOSFET, and without MOSFET, there would be no microprocessor, and without microprocessor, well, you wouldn't be watching this video. If silicon is so great, then why do we even bother with other semiconductors? Great question. Let's put them head to head. Let's start with gallium arsenide. Its electron mobility is about 6 times higher than silicon's electron mobility. That makes it incredible for higher frequency applications. Your 5G phone antenna, the receiver in a satellite dish, those use gallium arsenide because they need to operate at gigahertz frequencies, where silicon can't keep up. But, and this is a very big but, gallium arsenide manufacturing is so expensive. Its wafers are so fragile. And as we talked about, its native oxide is terrible. We can't build billions of MOSFET on gallium arsenide as we do on silicon. Next, we have gallium nitride. This one's a wide bandgap semiconductor, which has bandgap around 3.4 electron volts. It handles enormous voltages and power densities. That's why engineers are using this in fast chargers that can charge your laptop at better rate. Also, recently it's making waves in electrical vehicle inverters and radar systems. But again, gallium nitride's wafers are incredibly expensive to produce, and they are still limited in size. Growing a high quality gallium nitride crystal is much more harder process than silicon, and it does not have advantage of native oxide that we have for silicon. Next, we have silicon carbide, which is another contender of semiconductor materials. It handles extreme temperatures better than anything on this list. Its thermal conductivity is almost 3.5 times higher than silicon's. That makes it ideal for power electronics in harsh environments. But here is the pattern you might be noticing. Each one of these material is a specialist. Gallium arsenide for speed, gallium nitride for power density, and silicon carbide for extreme heat. They're like Olympic sprinters. Each of them are world class in their own event, but silicon is the decathlete. It's good enough at everything and cheap enough to put everywhere, and that's a combination that nobody else can match. But there is one more reason silicon is irreplaceable, and it might be the most powerful of all. It has nothing to do with physics, but it has great consequences, and that's economics. The semiconductor industry has spent over 60 years and billions of dollars optimizing every single step of silicon manufacturing, growing perfect crystals using Choklahal-Skid process, slicing them into wafers, then lithography, etching, doping, packaging. Every process has been refined to an almost absurd level of precision. A modern fab can pattern these features just a few nanometers wide on a 12-inch silicon wafer. The yield, the reliability, the cost of a per transistor, it's all been driven down to the levels that no other material can even approach. Think about it this way. Imagine every road in this world was built for cars with a specific wheel size. And now someone comes along and says, hey, I invented a slightly better wheel, but it doesn't fit in on any existing roads. How much would it cost to rebuild every road on the planet? And that's what replacing silicon looks like. Even if materials were objectively performing better in every single way, which is none of them are, the switching cost would be astronomical. This is why the industry's approach has been silicon plus, not silicon replacement. Use gallium nitride for the charger application, use gallium arsenide for the high frequency applications such as antennas, use silicon carbide for the power inverter, which are applicable in harsh environments. But the brain of every system, the CPU, the GPUs, and the memory storage, that is still silicon, and it will remain silicon for decades to come. So is silicon the best semiconductor? No, not at speed, not at power density, not at heat resistance. But is it irreplaceable? Absolutely. Because being the best at one thing was never the game. The game was good enough at everything, cheap enough for everyone, and reliable enough to bet an entire civilization on. And that's exactly what we did. So next time, if you pick your mobile phone or open your laptop, remember, behind all of those technologies, it's all silicon. If you enjoyed this deep dive, please hit the subscribe button. I got a lot more engineering mysteries to unravel on this channel. And next time we are going to see how transistors turn on and off at the atomic level. And trust me, it's way more interesting than you think. See you then.